Last speaker of the session is A Lidar. And as soon as he's wired up, please.
Hello. Okay, good morning. Try to keep this fairly short and sweet. I realize I'm what stands between you and the coffee break. So I'd like to talk about new work we did. This is Tamim Albash and I on trying to find speedups on the D-wave machine. We call it evidence for a limited quantum speedup. And I have to say this is 95% Tamim's work. He should have been the one presenting this, but I'm glad to do it in his place. So let's start with what is a quantum speedup. I just want to make sure that we're all on the same page. This shouldn't take long. A quantum speedup is not a prefactor or an offset. It's not some constant multiplicative factor that we sometimes see, but instead it is a quantum advantage that grows as we make the problem bigger. Right? So it's the standard notion of what we've always called quantum speedups in this business. It means either a lower exponent or perhaps a lower degree polynomial. So this is the kind of speedup that I'm interested in. Now, unfortunately, despite many years of work in quantum computing, as we know, we currently do not yet have evidence, experimental evidence, of a quantum speedup. It just has never been observed. And that's not for lack of trying. It's just very, very hard to get there. So in light of that, it makes sense to lower the bar a little bit and try to settle for less. And in some contexts, people talk about this as demonstrating quantum supremacy, which is still a very high bar. And I want to lower the bar even more. I want to talk about the idea of a limited quantum speedup, which was introduced in this paper by Rano et al. So what is a limited quantum speedup? Suppose that we have some quantum hardware that runs a quantum algorithm and it solves some problem P. And now let's say that we have a classical computer that also solves the same problem P, and it uses an algorithm, or maybe several algorithms, that are similar in the sense that they implement a similar algorithmic approach. Right? So a good example to keep in mind here is, let's say this is a quantum annealer, and let's say that the classical computer runs simulate annealing or spin vector Monte Carlo. So these are classical algorithms that correspond to the quantum annealer, and they run a similar algorithmic approach. So this is the kind of comparison that we want to make. So what is a limited quantum speedup in that context? It's when we can demonstrate that the quantum annealer runs faster, but in the sense that I defined earlier, right? So in the sense of a scaling advantage, not of a constant factor type advantage. And if that's the case, if we have a correspondence, this is a classical version of the quantum algorithm running here, and we have a better scaling observed on the quantum hardware, then that's what we call a limited quantum speedup. Okay, so that is a lower bar than a genuine or an unqualified quantum speedup. And it's a lower bar because there's an obvious caveat, which is that it's quite possible that there are other classical algorithms that can outperform the classical algorithms we ran here and possibly even outperform the quantum hardware. All right. So this is the kind of result that we're shooting for here, with a caveat understood. Okay, now here's the thing. We don't even have an experimental demonstration of a limited quantum speedup yet. And what are some of the reasons for that? Well, obviously there's the issue of decoherence and noise, which we need to mitigate using quantum error correction. But that's not what I want to focus on in this talk. I'd like to focus on the problem of annealing times being too long. And that, of course, is a problem that is specific to quantum annealers. It's what I'd like to call the curse of suboptimality. So to make that precise, what is the issue with annealing times being too long? I have to very quickly explain how we compute the time to solution. The time to solution is the time that's required to find the ground state at least once with probability 99%. That's how we define that. So more specifically, suppose we have a quantum device that we run with some annealing time, T sub A. We measure the probability of the ground state. I call that PGS. And then the time to solution is simply the time per run, the annealing time, times the number of repetitions. Okay, and it's easy to show that the required number of repetitions is given by this formula here. Probably a well-known formula to most people. So what is the optimal annealing time? The optimal annealing time is simply the time that minimizes the time to solution. And because there's a T sub A here and a T sub A here, you see that there's some non-trivial interplay between the two, and it's non-trivial to minimize this quantity. But this is what we call the optimal annealing time. It's the run time, the single run time that minimizes the time to solution. Now, I'd like to be very emphatic about this. One cannot trust scalings reported unless an optimal annealing time has been identified. Right? This is like a certificate for a trustworthy time to solution or a trustworthy scaling if you've identified the optimal annealing time. If you haven't, then you have a problem. So here's a kind of an extreme example to illustrate why you have to identify the optimal annealing time. Suppose that you use an annealing time that is so large that with a single run, you always get the same success probability. Okay, so if that's the case, and this number here is 1, then the time to solution is just the annealing time. It has no size dependence, problem size dependence, and that can't be right. Right? So if that doesn't convince you, then here's a simulation to illustrate the problem. So suppose we run simulated annealing on some problem class, doesn't matter exactly what it is in this case. Time to solution as a function of problem size. Here, this is on the chimera graph. And let's say that we run suboptimally, meaning we fix the number of sweeps for simulated annealing, and we deliberately pick the number of sweeps to be too high. So then you get this blue set of data here. And you see that relative to the optimal number of sweeps, where for each data point here, we've optimized the number of sweeps. We've minimized the time to solution for that particular number of sweeps. You see that you get a scaling that is too flat. Right? And this is the false scaling. This is the true scaling. Right? So if you run too slowly, if your annealing time is too slow, you would fool yourself into believing that you have a nice flat scaling. But it's not the true scaling, because you didn't minimize the time to solution per data point. Right? So this is the danger of not optimizing the annealing time. You can fool yourself into believing that you have better scaling than you really did. In the example that I gave on the previous slide, right, so this example, what happens is you get a perfectly flat line, which of course can't be the true scaling either. Okay, so scaling curves without an optimality certificate simply cannot be trusted. Right, and this has vexed us for the longest time with the D-Wave experiments that we've done on benchmarking. And finally, thanks to Tamim's ingenuity, we were able to demonstrate an example of a class of instances that exhibit an optimal annealing time. So the smoking gun is when you see a minimum in the time to solution as a function of the annealing time. Right? And here is the experimental evidence for a class of instances that I'll tell you about in a second. Time to solution as a function of annealing time, and what we're looking for is a minimum. Right? So the minimum is the optimal annealing time. And lo and behold, here for different sizes, so L is the linear dimension of the chimera graph. It counts the square root of the number of unit cells. So starting from 12, this is on the D-Wave 2000Q. Starting from 12, you see that for every size, we are able to identify a minimum, i.e. an optimal annealing time. Okay, and now it's kind of interesting to try to speculate what's going on here. So in my ideal world, this decrease in the time to solution as a function of annealing time is a signature that we're adiabatic. So as you increase the success probability, a decrease in the time to solution is an increase in success probability. So as we increase the annealing time, the success probability goes up, which is what you'd expect from adiabatic dynamics. But then why does the time to solution start to go up or the success probability go down? Maybe because due to decoherence. So we're not sure what's going on here. This could also be the decrease in time to solution could also be because of relaxation assistance. It's not clear what's going on here. That's a very interesting open question. But the point is we now have this certificate of optimality, which we were looking for this particular class of problem instances that we call logical planted solution instances. So Helmut, in fact, already described it. We do this trick of creating a spin glass backbone by tying together unit cells ferromagnetically and then introducing frustrated loops that connect these unit cells. We call this the logical planted solution instances because we're actually looking at the logical graph which is formed by collapsing each one of the unit cells into a single node. And then that's step one. This is a well-known construction. And then step two, which is a new feature of this work, is that we take a gadget which has this particular form. The blue lines here are ferromagnetic couplings, and there are two anti-ferromagnetic couplings here which create frustration. And then there are also local fields, local magnetic field biases on each one of the qubits. So we take one of these gadgets. This gadget has some nice properties that I don't have time to get into. And we sprinkle these gadgets randomly on the chimera graph. What seemed to work was to take 10% of the unit cells and sprinkle these gadgets on them at random. And that's the construction. This is what we call logical planted solution instances. The word planted is because they also have the nice feature that each one, that in all cases the ground state is planted. We know it in advance. Okay, so that's the problem class. So now I come to the scaling results. All right, so now finally we have the ability to deliver scaling results that have a certificate of optimality, so we know we can trust them. So first, here are the two classical solvers that we're going to try to beat in order to demonstrate a limited quantum speedup. And so this is simulated annealing and spin vector Monte Carlo. Simulated annealing, I'm sure I don't have to introduce. Spin vector Monte Carlo is this algorithm that Shin, Smith, Smolin, and Vazirani came up with in order to give a classical model of the D-wave machine. Instead of, as in simulated annealing, thinking of each spin as a plus or minus 1, in their version, in SVMC, each qubit is replaced by a 2D rotor. So there's an angle associated with each qubit. And these angles are updated with metropolis moves. And in addition, the dynamics follows the D-wave annealing schedule. So this model was extremely successful in reproducing ground state distributions that were experimentally measured in some of the earlier work that we did on plus minus 1 spin glasses, plus minus 1 random instances on D-wave. So it's become kind of a model to beat, a physical model to beat of the D-wave machine. It wasn't actually designed as a solver initially, but it's become an interesting solver as well. Okay, so this is just the results of simulated annealing and spin vector Monte Carlo, how they scale on this problem class that I just defined. So again, time to solution on a log scale, and the square root of the number of chimera unit cells. So time to solution is the following problem size. And you see that except for some, well, call it finite size effects at small l, the scaling seems to be well described by an exponential. So we fit these curves to an exponential form, and we can fit the scaling coefficient. And this is the 95% confidence interval. And okay, this is what the scaling coefficients are for simulated annealing and for spin vector Monte Carlo. And by the way, what I'm showing you here is the median. We also have results for different quantiles, but essentially they're the same. Now comes the punchline. All right, so here's the D-wave scaling. And this is now, again, certifiable, optimized scaling. And so each data point here corresponds to the having optimized the annealing time so that we know that this is the true time to solution scaling of D-wave. And we find a win in this case for quantum annealing, or for quantum annealing as implemented via D-wave. As you see, it's kind of hard to tell by eye, but if you extract the scaling coefficient, it is lower to within 2 standard deviations confidence. It is lower than both simulated annealing and spin vector Monte Carlo. All right, so that is the first example that I know of a limited quantum speedup demonstration. Unfortunately, the news is not all good. There is a classical algorithm that is better, and this is simulated quantum annealing, quantum Monte Carlo, and it is substantially better. Here is the scaling coefficient for SQA, and it's easy to tell by eye in this case. Right. So it's not quite a home run yet, but at least we've beat, or D-Wave has beat, these 2 classical solvers, simulated annealing and spin vector Monte Carlo. So is there hope here to defeat SQA? And I think there is hope. We have to remember that the classical algorithms run on extremely reliable classical hardware, so they don't suffer from errors at all. Of course, in the case of the D-Wave machine, there's still plenty of room for error reduction. And we can expect that with future generations of machines, not of people, that the quantum annealing scaling may improve, and I can only hope that it might match or exceed SQA. And also that with new examples of instance classes, we might hope to see, like the ones that Helmut and Salvatore were talking about, we might expect or might hope that the D-Wave scaling will improve relative to SQA. Okay, thank you.
Thank you. Please.
So, would you say that all previous studies testing quantum speedup are not very much reliable in the sense that they didn't measure at the right time?
Yes.
Oh.
Okay. Including my own.
Yeah, the SQA has extra variables, right? I mean, isn't the point that the SA and the SVMC have the same number of variables, so they look and feel a little bit more similar to what the quantum thing does? But the SQA, you have a whole extra set of variables. Am I right or no?
I'm not sure what you mean by extra variables.
Well, don't you have to,
there's a temperature.
Yeah, don't you have, how many variables do you have in SQA? Do you have N, or do you have to then multiply? Is it more? Just help me out.
Well, there is the temperature dimension, the imaginary
Yeah,
time
that's
dimension.
what I mean.
Yes.
So do you introduce variables for that? No. Just help me out. What?
Yeah, so I mean, there are all sorts of update rules you can apply. I mean, I'm not sure if that's, so maybe you should ask the next question.
No, that's it.
Oh, okay. Yeah. So now I think it's a fair comparison with SQA. We've optimized the number of sweeps here, and it's all, SQA is running optimally as well.
So for once, I have 2 questions. The first one is, I assume, tacking onto the question from Eddie, that you're running SQI in the continuous time limit.
Thanks for that. No, this is discrete time SQA, and discrete time SQA is with 64 time slices.
So basically, it's a classical solver.
It is a classical solver. It's not a model, really, of D-Wave. So in that sense, it is not in the same class as simulated annealing SVMC here. It is not really a simulation of D-Wave. If we did continuous time SQA, it would be a different story, but we can't do it for...
with D-Wave. That just can't.
Well, okay, fair enough. But in the early days, like early days was only 4 years ago, people thought that SA was a wonderful model of
okay,
D-Wave.
we don't have to repeat what people thought if it was wrong. I mean, SA is just not a simulation of quantum processes. It isn't.
So my other question is, since you did not run it in the continuous limit, how does it compare to other algorithms?
Yeah, so we did test it against HFS and against what we call SA with cluster updates, or which you call superspin. And against HFS and against the simulated annealing with cluster updates, they also beat D-Wave, but SQA beats everybody, which is why I focused here on SQA.
Okay.
But the thing about HFS and the other one is that again, they're not simulations of the dynamics of
Sure.
what's going on here.
The last question by Ryan in the back, and then one for...
Hi. Doesn't your equation for time to solution kind of assume some independence about the runs? And
Sure.
how do you know you're not getting fooled by metastable states, for example?
Yeah, so you're right, that it does assume independence of runs, but and we actually also know that the runs are not totally independent, that they are slightly correlated. But this is a very weak effect. This is something that we did look into.
And is that quantified anywhere in the graphs or in the paper?
No, not in this work. This was done in earlier work.
So after Brian asked, it's time for Ryan.
Okay, so you may have actually mentioned something about this, which I missed, but if you were to consider the determination of the optimal annealing time as a pre-processing step that was essentially part of the algorithm, how would you incorporate that into the scaling?
Yeah, but I won't answer that directly because we also have to do that for all the classical algorithms.
Agreed,
right?
completely.
Okay.
But
okay.
it still sort of feels like, that's kind of a caveat to saying that this is always how you have to look at the scaling.
Well, but it doesn't change the scaling because it's essentially kind of a grid search that you have to apply equally for every solver.
Okay. So I suppose you're saying then that you would use the same sort of pre-processing to determine optimal parameters for all the algorithms. But potentially if certain algorithms had more hyperparameters than others, this determination might be more costly.
That's true. So you can talk about, for example, optimizing the not the annealing time, but the schedule itself. Right? And that's a rabbit hole we did not go into, but I'm sure we will now that D-Wave has made this possible.
Good. Then I'd like to close the session and thank all the speakers again.